Hello and welcome to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Sana, I'll be one of your hosts this evening, and I'm joined by Quinton. We're broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts every Monday night at 9 p.m. local Toronto time or Tuesday morning at 2 a.m. Universal time. The York Universe production works in concert with our online public viewing program run by the Observatory team, which runs between the hours of 9 to 10 p.m. local Toronto time. We're currently showing some archival images taken by our Observatory team on our OPV, including images with our 1-meter telescope. For any questions or comments you may have on our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. Alternatively, you can also connect with us on Twitter at the handle @York Observatory, on Instagram with the handle @YorkU Observatory, and on Facebook at Allan I. Carswell OBS. All of our programs are free, but if you would like to make a donation, please see our website at yorku.ca/science/observatory. We'll be monitoring the chat rooms for questions and to post content. But apart from that, we are good to probably get going on our show tonight. So Quinton, how are you?
I'm very well, thank you. How are you, Sonny?
Oh, pretty good, pretty good. Unfortunately, not having some great weather right now. I'm not sure how it is where you are, but we're getting this like that annoying like rain snow hybrid right now. So,
Yeah, on my drive home from the university, it was raining for like 90% of the drive, and then right near the end, it turned into snow. And I think
oh,
it's still snowing. So personally, I don't know, maybe this is a controversial opinion. I'm in favor of the snow. I think that it's December 18th. I think it's about time we got some actual snow. It's been a very green December this year. And I, I mean, it's not great to drive in. I don't want necessarily a lot of snow, but I'd like to at least see some snow, you know?
I agree. I agree. I know there are probably some people, even some staff in the OPV who would disagree with us, but uh, I
Okay,
agree. I agree.
as an astronomer, of course I would prefer it to not have any precipitation. But the way I see it, if it's winter, if it's gonna do something, it might as well be snow and not
Oh yeah, yeah, I agree. It's just been annoying this week getting all this rain. Like,
rain. Yeah.
how is it this warm in December? But like,
Global warming.
yeah,
Yeah.
yeah. It'd be
Well,
nice to get at least like one good dumping of snow around this time, just once,
yeah, I
so
mean
we can have that winter wonderland.
the good news is that given the way some of the past winters have gone, we'll probably get just an excessive amount of snow all the way from January to like April. So
Yeah,
you never know. You never know. It's
yeah,
someone set the weather to the random setting lately.
yeah. In like 3 or 4 months, we'll be having a conversation of I hate the snow and I'm so sick of it, and
I have not
probably is what's
seen the
gonna happen.
ground for the past 4 months.
Yeah. Yeah, well, hopefully we do get some clear skies mixed in there so we can do some observing. But um,
Absolutely.
yeah, the weather's been kind of terrible the past couple weeks for observing, but we have got a couple nights in there. So um, yeah, hopefully we get a couple more.
All right. Now, I believe that I have the first this week in history item. Did you want to
Yes,
proceed?
you do.
Oh, okay,
Yeah, yeah, go ahead. You got the first
fantastic.
one.
All right. So last Saturday marked the 166th anniversary of the birth of Edward Emerson Barnard, who was an American astronomer best known for the discovery of Barnard's star in 1916. So Barnard was born in Nashville, Tennessee on December 16th, 1857, to an impoverished family who could not afford to give him much of a formal education. He was actually raised by a widowed mother. His father passed away 3 months before he was born, which is part of the reason why, unfortunately, his family didn't have very many resources growing up. But he took an interest in photography at a very young age. He became a photographer's assistant at 9 years old. He later developed an interest in astronomy, and he purchased his first telescope in 1876 when he would have been around the age of 20. So despite his lack of formal education, Barnard was able to discover more than 5 new comets over the course of the 1880s, which earned him enough reward money to build a new house for himself and his wife. Barnard's impressive work earned him the respect of the other amateur astronomers in Nashville, who raised enough money to give him a fellowship to Vanderbilt University. And while Barnard didn't graduate from the school, Vanderbilt did give him an honorary degree. He remains the only person to have received an honorary degree from Vanderbilt University to this day. So he joined the Lick Observatory in California in 1887, and in 1892 he observed a nova, and he was the first to notice its gaseous emissions. And he surmised from this that it was caused by the explosion of a dying star. He also discovered Jupiter's moon Amalthea, and he was the first person to discover a moon of Jupiter since Galileo observed Io, Callisto, Ganymede, and Europa way back in 1609. So those were the first moons of any planet other than the Earth to be observed. And then there was a period of roughly 400 years in between that and Barnard's discovery of Amalthea, in which we didn't know about any of Jupiter's other moons. And of course, nowadays we know that Jupiter has dozens upon dozens of moons. I think over 100 last I checked. There's certainly more than 80. And in any case, in 1895, Barnard joined the faculty at the University of Chicago, which is where he worked when he discovered the star that bears his name in 1916. That's Barnard's star, which is perhaps his most well-known achievement. So Barnard's star is a red dwarf. It's the fourth closest star to the sun, after the 3 components of the Alpha Centauri system. It's also the closest northern hemisphere star to the sun, and it's about 5.96 light years away, which is very close in astronomical units. So Barnard observed that this star, which is in the constellation of Ophiuchus, and it's invisible to the naked eye, had a very large proper motion relative to other stars. So in other words, it appears to move relative to the other stars in the night sky at a rate of around 10.3 degrees per year. So none of the stars' positions are fixed in the Milky Way. They do move on their own independent paths through our galaxy, just like the solar system itself does. However, because of the sheer size of the Milky Way and the distances between stars, their motions relative to us and to each other are typically far too subtle to see, and they take centuries to be detectable with the naked eye. So Barnard's star is an exception due to how close it is to the sun. This means that it appears to move much more quickly than more distant stars. You can kind of think of this similarly to, like, if you're on a road trip and you're looking out the side window of your car, you'll see that the fence posts along the side of the road appear to move past you a lot more quickly than the mountains way off in the distance. In reality, your vehicle is moving at the same speed relative to both of those things. Because the mountains are so much further away, their apparent motion is a lot less. So Barnard passed away on February 6, 1923, at the age of 65. And while he died at a relatively young age, his legacy lives on through his many contributions to astronomy and the many objects and locations that bear his name, such as the nebula Barnard's Loop, craters on both Mars and the Moon, the feature Bernard Regio on Ganymede, Bernard's Galaxy, which is NGC 6822, the asteroid Bernardiana, a residence hall at Vanderbilt University, and of course, his namesake star, whose name was officially recognized by the International Astronomical Union in 2017.
Well, I think you've given me a couple new targets for the 1 meter, because I want to observe like Barnard's star and Barnard's galaxy now.
Absolutely.
After hearing about him, yeah.
I'm really
Yep.
interested in Barnard's life, because this is an example of a person who really didn't have very many resources to work with. He was very poor, didn't have much in the way of formal education, and was still able to achieve these great things simply because he was extremely passionate about astronomy. He kind of made it his life's work to do all the research that he could, and fortunately for him, he was recognized by the other people in his area who helped push him to succeed. So he's a real astronomical success story, kind of I don't know about a rags to riches story. I don't know how much money he had when he passed away, but certainly a success story, which I think it can be really inspirational for anybody else who's interested in getting into astronomy.
Yeah, absolutely. It's really remarkable how much he was able to do just in general, but especially when you factor in his background and how he didn't have a lot of money growing up. It really is remarkable how much he was able to accomplish in his lifetime.
Absolutely, absolutely.
Yeah, I still can't imagine observing and doing science like this back in like the 1880s and during that time period. It makes me feel like we're almost kind of spoiled now with all of the cool astronomy technology that we have now. Like even the backyard telescopes that you can buy, you can have these go-to systems on them to kind of drive you wherever you want. But to be able to actually just use telescopes and like your love of astronomy and just look to the stars and find new things like he was able to. It really is, like you said, like he really was passionate about astronomy.
Yeah, it was a period when the technology that we rely on so often now was really still in development. I have another historical item a little bit later on that'll kind of touch on this as well. Uh, it's it's really impressive how far we've come. Astronomy as a I mean, astronomy is in some ways one of the oldest sciences that humans have because every ancient culture has had some interest in the stars and some interest in keeping track of them and understanding them. But it wasn't until the past 400 years with the invention of the telescope that we really had any way to use anything more advanced than just like the naked eye to try to classify stars. And so many of the big developments that we now use every day were developed in the last couple centuries, in many cases, the last few decades. So it really is an example of a science that's I think still in its infancy, and there's still so much that so many avenues that we have yet to fully explore, like gravitational wave astronomy or neutrino astronomy, that are still in their infancy, I think, and I can't wait to see where the field continues to go.
Absolutely. Absolutely. I know there's a lot of like really cool like telescopes and everything that are going to launch or be built in the next like 10 years or so. But the point that you make about things like gravitational waves and neutrinos and how that can so widely expand what we know about astronomy is so exciting.
Absolutely.
Yeah.
Oh, okay. So speaking of, I guess, new and exciting telescopes. I'm looking at your next item. I'm sure this is related. This is one that I'm glad we're talking about because this is an achievement that I'm honestly still not over us having managed to do like 2 years on. So please take it away.
Yeah, so this I don't know about you, but to me it feels weird that this was only 2 years ago. It
Yeah,
feels like less than 2 years in a way, but also more than 2 years in a different kind of way, if that makes sense. But almost 2 years ago now, December 25th, 2021, finally the launch of the James Webb Space Telescope. So, just a bit of basic facts about James Webb. It is a 6.5 meter diameter infrared space telescope. It's primarily run by NASA, but it is an international collaboration with some contributions from the European Space Agency and the Canadian Space Agency. Now, James Webb is the largest and the most complex space telescope that was ever created and ever launched into space. It is like a feat of engineering. This thing is absolutely amazing. There were lots of, like lots of tests and lots of new things that had to be developed in order for JWST to actually be able to work, which translated into a lot of delays and kind of budget overages. But after $10 billion and many, many, many years, JWST did finally launch 2 years ago, December 25th, from French Guiana aboard the Ariane 5 rocket, which was part of the Europeans' contributions to JWST. Now, because JWST is the largest space telescope to ever be created, there had to be a lot of like creative engineering decisions that went into how the telescope was made. So particularly this thing is way too big to actually fit into a rocket and launch it into space. The primary mirror of the telescope, like I said, is 6.5 meters in diameter. There is no currently existing in existence rocket that will be able to fit a 6.5 meter diameter mirror into it. More so than that, JWST also has this massive sun shield. It's the size of a tennis court, and it's basically just designed to keep the optics of the telescope cold. So, being an infrared telescope, if any sunlight, which is basically heat, hits the mirror, it can heat it up and basically wash out signals from like faint galaxies or faint stars or nebulae. So if sunlight or even light from things like the moon or the earth hit the optics of the telescope, it essentially just becomes useless because it gets too hot to work. So engineers designed this like 5-layer sun shield that is the size of a tennis court that protects the optics, which is also way too big to fit into a rocket. Now, the solution that people ended up coming up with for this like size issue with JWST was to essentially engineer the telescope so that it can be folded up, stuck into a rocket, launched into space, and then once it's in space, clear of the atmosphere, clear of the rocket, it can unfold itself. I've heard it described as reverse origami quite a few times, where the sun shield, like, can get stretched out and tensioned into the right size. And the primary mirror itself even has different segments that can sort of collapse to the side so that it can fit into a rocket and then unfold when it's in space. So, following the launch, we went into this period of it was like the 29 days of terror for JWST astronomers, similar to how scientists who work on Mars rover missions have their 7 minutes of terror as the spacecraft or the rover enters the atmosphere of Mars. There's those 7 crucial minutes that it's going to land, that it's a 7 minutes of terror because you don't know if it's going to land or work properly. But for Webb, this was like significantly more complicated than any other mission that has ever flown into space. So we had the 29 days of terror, the 29 days where it went through multiple different deployments to fully deploy the telescope with 344 single points of failure. So these
I
are 300. Oh,
I
sorry.
couldn't imagine. I'm sorry. That's 29 days of just not knowing. Oh
Oh
my.
yeah, yeah, yeah. I followed it very closely. So if I was like panicked like that, I can't imagine how the like scientists and the people who spent their lives working on this thing was feeling. Um,
Yeah.
there was also a little hiccup with the sun shield deployment on one of those days where everything was fine, but one of the sensors like wasn't reporting that the sun shield had deployed as it should. So everyone was apparently kind of sitting around going like, did this break? Did this not work? Terrified that that was the end of this mission. But everything did turn out to be fine. They kind of figured out another way to look at it and figured out that the sun shield did deploy as it should have. So everything was okay. But yeah, it was 29 days of all of these different deployments and also waiting for JWST to reach the Lagrange 2 point. And this is a point in space. It's about 1.5 million kilometers away from the Earth. It's where JWST and a lot of other spacecraft spend most of their lives. It's kind of a really unique point in space where the gravitational force from the sun and the Earth kind of cancel each other out. So you can essentially put something in orbit around this empty point in space, and it'll just kind of sit there and do its thing and spend its life just in orbit around this point in empty space, which is where JWST is right now. So yeah, we had the 29 days of terror that ended up turning out great because everything worked. And then following that, there were an additional around 5 months of commissioning of the observatory, just aligning the telescope mirrors to make it work very nicely as one big 6.5 meter mirror, and getting the instruments online, cooling them, getting them ready to do science. So after all of that, the first images and the first science started coming out of JWST in July of 2022. And we're now around 2 years into its time and space, but only 1.5 years into its science. And this is the part that to me feels like should be more than 2 years, because there's so much awesome science that has come out of this thing. Way too much to be able to talk about, even if we devoted the entire hour to JWST science. But a couple of interesting things that I wanted to, or a couple of interesting science highlights out of JWST I wanted to point out is, so first of all, starting, I guess, with distant galaxies, which is one of the main science drivers for JWST, is it's now giving us the first look of what normal galaxies in the first billion years since the Big Bang looked like. This is a time called the epoch of reionization. It's kind of a transition point for the universe. It's a really important step in the evolution of our universe. And we're now, for the first time, learning what normal galaxies in that epoch look like and how they influence their environment and contribute to this evolution in our universe. It's also revealed some of the most distant galaxies ever known, out to around something called redshift of 13, which corresponds to when the universe was only 300 million years old. So these are truly some of like the very first galaxies that are starting to emerge in our universe that JWST is actually being able to find and learn about for the first time. It's also done a lot of really cool stuff in planetary science. So it's observed the popular TRAPPIST-1 system of planets. And so far, based off of observations of a couple of them, it doesn't look like these planets are habitable, which was, or could, maybe habitable is not the right word, but there were a couple of Earth-like planets that looked like they could have the potential to support life. But JWST has now ruled that out as a possibility for those two. They're much hotter than you would be expecting for a planet that could support life in that kind of way. It also made a really nice discovery of photochemistry on an exoplanet. So this was on the planet of WASP 39b. This is basically a Jupiter-sized exoplanet that is orbiting its star at around 5% of the Earth's orbit. So this is insanely close to the star. It's just getting hammered with radiation and heat from the sun, and that's made it very hot and kind of puffy. So when JWST took a spectrum of WASP 39b, they were not even looking for the signature at all, but it just popped out in the spectrum. It found evidence of sulfur dioxide, which is only produced through photochemistry. So this is when light has to come and interact with some molecule, split it up into different components, and then those components can then go on to make other kinds of chemicals. So what's happening with the sulfur dioxide is that photons, particles of light from the host star, are smacking into water molecules, splitting off some of the oxygen atoms, and then those go to make sulfur dioxide, which is pretty insane. This is the first time that it's ever been found on any other exoplanet. So pretty major discovery out of JWST. There's also been some really cool observations from within our solar system, including some investigations of, or some information on how Earth got all of its water. And even today, there were some new really cool images of Uranus that were released from JWST. So definitely a whole lot of really cool science that's come out of Webb. And I really can't wait to see what the next 10 plus years look like from Webb science. It should have enough fuel to operate for 20 years in total if everything goes well.
That's so cool. It's so cool. I love the James Webb Space Telescope. I know that the mission got delayed a few times in terms of when it was going to be launched. And
Oh yeah.
there was a part of me that was a little bit it's like, oh, is this thing ever going to be launched? And I'm sorry I doubted them. I'm so glad that we've got it operational now. All the science that this thing is coming out with is just so cool.
Yeah. I'm really glad actually that it launched on December 25th, because it's
Yeah.
literally a Christmas present for astronomy.
It really
So
is. It really is. It's
yeah.
poetic.
Yeah, so I was pretty happy about the December 25th launch date. But speaking of some of interesting discoveries, you have a different discovery to talk about in our next item.
Yes, I do. And I wanted anybody listening, I want you to keep the JWST in your mind, because I have another item a little bit later on, which is also kind of related to this. But I want to talk about, first of all, I want to talk about December 22nd, 1891. this was when Max Wolf discovered his first asteroid, 323 Brucia. So Max Wolf was a German astronomer born on June 21st, 1863 in Heidelberg. He pioneered the technique of using astrophotography to automate the process of discovering asteroids. So up until this point, asteroids were discovered through visual observation, which was a labor and time-intensive process. Instead, Wolf figured out you could use an astrograph, which is a telescope specifically designed to capture astrophotography images. You could take a long exposure of a particular part of the sky, and any asteroids that happen to be in that image would appear as short streaks instead of single dots because they're orbiting the sun, which causes them to move relative to the stars in the background. So if you remember from the section where we were talking about Barnard, I talked about this concept of proper motion. Well, asteroids, because they are part of the solar system, and because they orbit the sun, they have a high degree of proper motion. So they appear as a streak in any kind of long exposure image. The Heidelberg Observatory, it had a double astrograph, which had been paid for by a generous grant from the American philanthropist Catherine Wolfe Bruce. The Wolf in her name is unrelated to Max Wolf. They're completely unrelated. It just seems to be a fairly common name at the time, although they have different spellings. So Wolf named the first asteroid he found with the astrograph Brucia after Captain Wolfe Bruce. Brucia is approximately 33 kilometers in diameter, and until July 2017, its orbit crossed the orbit of Mars. Since then, it has evolved so that it no longer crosses Mars's orbit. It merely approaches or grazes it from the outside. So Wolf would go on to discover 248 asteroids over his lifetime. He also applied astrophotography to the study of stars, and this was a technique which his contemporary, Edward Emerson Barnard, was also using. So the two of them were engaged in similar fields of research during their careers. Both men performed extensive research on low luminosity stars with large proper motions, and in fact, Wolf published a catalog of over 1,000 such stars. So the most famous of these is Wolf 359, which is 7.86 light years away from the sun. So this is also very close in astronomical distances. Only the Alpha Centauri system, Barnard star, which we talked about earlier, and a pair of brown dwarfs called Lumen 16 and WISE 1049 5319 are known to be closer than this. So Wolf 359 is an extremely dim red dwarf, even dimmer than Barnard star. Wolf 359 has a magnitude of 13.54, and Barnard star has a magnitude of 9.51. The magnitude of a star, the larger the number is, the dimmer the star is. Wolf 359 is located in the constellation of Leo, and it has a proper motion of 4.696 arc seconds per year. So this is a lot less than the 10.3 degrees of proper motion that Barnard star has. This is still quite a large proper motion compared to most of the other stars in the sky. Max Wolf died on October 3rd, 1932 at the age of 69. And in addition to his catalog and the stars within it, Max Wolf is the namesake for the Wolf crater on the moon, as well as the asteroids 827 Wolfiana, 1217 Maximiliana, and 1152 Pavona, whose name is based on a portmanteau between his name and that of his collaborator, Johann Palisa.
So this is the guy or the person that the Wolf catalog is
yes,
is named after.
The creator of the Wolf catalog.
Yeah,
and kind of circling back to what I was talking about earlier with Edward Barnard, we see here that like some a field that we at the Allan Carswell Observatory work with all the time, which is astrophotography. Like if anybody is in the online public viewing room right now, you're looking at a bunch of astrophotography images that we have captured and keep in our archives. This is a pretty new field of research. It wasn't until the 1890s that researchers were using astrophotography images for the purposes of detecting objects with high high proper motions, like asteroids and particular stars. So this was a field that was very much in its infancy because um, the the astrograph needed to be invented. You needed to invent a telescope that was able to hold still for long enough to create a long exposure shot. So I remember, I don't remember exactly which episode it was, but it was definitely one of the ones that I was on. We talked about some of the first astrophotography images which were taken, the first star that was captured in a photograph, other than the sun, was Vega. And the process of capturing even a really bright star like Vega at the time was very complicated because it was so difficult to track the star across the sky in a smooth manner in order to get a clear image. This is coming back to what I was talking about earlier about like how far we've come. This is a development that happened just over a century ago, and now here we are. We've put spacecraft in at the Sun Earth L2 point that just do astrophotography all the time and are dealing with incredible amounts of data that Barnard and Wolf couldn't possibly have imagined. So it's incredible to think about how quickly things have changed in this field.
Oh yeah. Yeah, there's even this is also making me think of the Vera Rubin Observatory, which is going to be coming online, I think, like next 5 or 10 years, that it's going to be just like this continuous monitoring of the entire night sky. And one of the big like science drivers for this is to basically use like this method to look for things like asteroids and comets and of course other things like these sort of like supernova explosions and stuff. But the whole sort of point of this telescope is to just take wide field pictures and be able to look for these sort of weird one-off transient events, including things like asteroids. So we're definitely still like feeling the effects of the science that was done by people so many years ago. Yeah, it's
Absolutely.
pretty cool.
Yeah, really
Yeah,
is.
yeah, yeah, which is also still very recent, even though it feels like long ago. It was definitely recent. Um, but moving on to our next news item, another December 25th item. But this time it wasn't a launch. This was December 25th, 2003, which was when the Mars Express spacecraft actually arrived at Mars and was inserted into orbit around Mars. So this was a European Space Agency mission and was ESA's first mission to another planet in general. The general sort of science goal for Mars Express was basically to explore the planet Mars, which hadn't really been explored too much at that point. It had 7 different instruments on board and was essentially just going to explore things like the atmosphere of Mars, the surface, and also trying to learn whether or not Mars had any sort of subsurface water or ice underneath its surface. The Mars Express, or kind of an interesting thing here, is that the Mars Express name came kind of from two things. It was a pretty fast spacecraft, so the Express comes from the like speed and how long it took the spacecraft to actually get to Mars. The European Space Agency took advantage of this close approach that Mars has. Most space agencies, when they're launching to Mars, actually do take advantage of this close approach. They happen once every 2 years. I remember during COVID, there were lots of Mars 2020 launches. I think like 3 different nations launched spacecraft to Mars because it was just the easiest time to do it. Mars is closest to the Earth at that point, so it's kind of easier to get spacecraft over there. But not all of these close approaches are equal. There are some close approaches that are extra close, and in 2003, there was an extra close approach from Mars. Sorry, that sounded weird. The 2 planets were closer together than they had been in around 60,000 years. So definitely a very good time to launch to Mars. The European Space Agency took advantage of this and then launched Mars Express on June 2nd, 2003, taking it only around 6-ish months to reach Mars, which is about a month or so faster than most Mars missions can get there. So Mars Express was a hugely successful mission. They did have a lander associated with the orbiter, which is called Beagle 2. But unfortunately, Beagle 2 failed when it reached the surface. It just didn't work. So the lander was just never worked. But the Mars Express, the orbiter itself, was very, very successful. It accomplished multiple science goals, including discovering ice at the south polar cap of Mars and possibly having discovered lakes of water underneath the south polar cap. This discovery is still kind of debated, so can't really claim it did detect it, but it did provide possible evidence for a water lake under the south polar cap of Mars, which is pretty cool. It was also the first spacecraft to detect methane in the atmosphere of Mars. This is another thing that was highly debated at the time that ESA did a press release saying that they found methane in the atmosphere of Mars. However, this was later confirmed by the Curiosity rover. So it seems that this methane detection in the atmosphere is legit. That said, the weird thing about this is that there was another spacecraft around Mars that did not find any evidence of methane. So again, this is another tentative detection, except kind of weird that two spacecraft found it and only one didn't. So I don't know. To me, it seems pretty legit. Either this interesting discovery either way. It also has made very detailed maps of the surface of Mars, which it has periodically updated over the years. It is still operational today and still updating these maps. It even has been serving as a relay for some rovers on Mars and continues to do a lot of really interesting science, even like over 20 years later. This was despite the mission being designed to last only for a single Martian year, which is around 687 days, Earth days. So hugely successful mission. And kind of fun fact about Mars Express, it was even the first spacecraft to do a live stream from Mars, where ESA did a really cool, it's about 1 hour long live stream of the planet Mars from one of the cameras in June 2023 to celebrate the 20th anniversary of its launch.
Oh, that's awesome.
Yeah,
Yeah, sorry.
no, go ahead.
All of these like early all of these like SpaceX these planetary exploration missions. I don't know what it is about them, but they really fascinate me. When I was doing the research for this episode, I ended up reading the show notes from last week where we talked about the Venera 7 mission to
Mm-hmm.
Venus. And I don't know. I've just got a big soft spot for planetary exploration in general. This is just so cool to me.
Oh,
We
me
always
too.
find something. We always find something. It's so cool.
Oh yeah, especially because like you learn so much more about a planet when you actually go to it versus just like observing it with telescopes. There's
Mhm.
just so many cool things.
All right.
But yeah.
I have one more this week in history item which I'd like to talk about before we move on.
Yep.
So earlier, Sana, you talked about the JWST. I wanted to talk about the JWST's roommate, as it were. I am, of course, referring to the launch of the Gaia satellite, which launched on December 19th, 2013. Roughly about 8 years prior to the launch of the JWST. So this was 1 decade ago tomorrow. Was when the Gaia satellite was launched. So Gaia is a space observatory built by the European Space Agency, and it's designed to measure the positions, distances, and motions of stars, as well as to detect exoplanets. It is located at the Sun-Earth L2 Lagrange point, the same place where the JWST is now located. So they're kind of sharing that region of space. And what this means is that it is located 150 million kilometers behind the Earth from the sun's perspective. As Sana was saying earlier, this is a region of space where the gravitational influence from the Earth and the sun kind of cancel each other out. So you can exist in a stable orbit around this particular region. There's four other Lagrange points for the Sun-Earth system as well. So over the past decade, since it began operation, the Gaia spacecraft has detected tens of thousands of asteroids and comets within the solar system. thousands of Jupiter-sized exoplanets outside the solar system, and 500,000 quasars outside the Milky Way galaxy. It has also compiled a massive database of stars within our galaxy, along with their motions, luminosities, masses, temperatures, and elemental compositions. The stars Gaia is able to target represent around 1% of the total population of the Milky Way galaxy. Gaia is expected to run out of propellant in 2025, at which point it will no longer be able to be precisely pointed at specific targets. However, its systems remain in good condition, and it is expected to be able to continue in its post-operations phase until 2030. Gaia, like all the other spacecraft we launch, gets worked hard, collecting data for as long as technically possible, even after it runs out of propellant.
Yeah, I mean, you got to just use these missions until you really can't anymore. And it's great that so many of these missions can last decades like this, like Gaia, and fingers crossed, JWST.
Now, I do see there's a question somebody asked if the observatory is open for public viewing on Wednesday. Correct me if I'm wrong, Senna, it's not open this Wednesday, right? Because we're going on our holiday break soon.
Yeah, no, it's not open for the next couple of weeks. We actually had our last public tour last week, but we will be opening up again in January. I'm not sure of exactly what dates we're going to be having. We're going to be open again, but we will be opening back up again in January on Wednesdays.
We appreciate the question. Thank you.
Yeah. All right. Well, for those of you who are just tuning in, you're currently listening to York Universe, broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. You've been listening to myself, Sana, and Quentin, currently discussing some This Week in History items. Before we get to our interesting news items for this week, I do have a couple of reminders for everybody. First off, this is our last show of 2023. Just like with the public tours, we are not running York Universe or OPV for the next two weeks, I think it is, because of our winter break. But we will be back on January 8th, 2024 for more York Universe and more online public viewing. So fingers crossed for some clear skies for those broadcasts and our in-person tours as well. For anybody who's looking to do some observing over the next couple of weeks, please note that there is the Quadrantids meteor shower. Is that how you say it? Quadrantids, I think.
Yeah, quadrantids.
Quadrantids, perfect. Which are peaking overnight on January 3rd to 4th. So this is one of the really nice meteor showers that happens every year, and is also kind of a unique one. While most meteor showers have peaks that last generally a whole night, the Quadrantids meteor shower peak is only a couple hours overnight on January 3rd to 4th. No worries if you can't catch the peak itself. You will still be able to see lots of meteors on for, I think it's probably a few days, maybe a week or so on either side of the peak. But if you do manage to get it during the peak, definitely recommended, because you can see close to 120 meteors per hour if you're in a dark sky site. So I think I'll definitely be trying to catch this one. Probably won't be too lucky with the light pollution around Toronto. But we did actually go try and watch I think it's the Geminids meteor shower a couple weeks ago, and you can definitely see some nice ones, even from light polluted areas. And this is a little bit further ahead, but 2023 kind of flew by for me. So a general reminder to anybody who is feeling similar things is that there is a total solar eclipse in April of 2024, which is now only 4 months away. So if you are planning to see that and you need to travel for it, that's probably something to start thinking about now. Yeah. And I definitely need to start thinking about my plans for 2024 eclipse.
Yeah, definitely. For anybody who's listening to this program from Toronto, Toronto is just outside the path of totality. So if you're willing to, if you do want to see a total solar eclipse, again, assuming the weather is good, we have no idea, right? It's 4 months away.
Oh my God.
Yeah, that'd be a real shame, wouldn't it, if it was all clouded out.
Oh yeah.
But if you do want to see a total eclipse and you live in Toronto, you may need to travel, but you probably won't need to travel far. I believe, if you go even south to Hamilton or even further south to Windsor, you will be in the path of totality. And that's a few hours drive. Just keep in mind, probably a lot of other people have the same idea. So anticipate traffic if you plan to do that.
Yeah, and hotels if you need to travel any further. Like there's probably a lot of hotels already booked up by now. So yeah, but I think traveling a few hours for a total solar eclipse is definitely worth it. So I will be trying to observe it, fingers crossed for clear skies. But back to more recent news, we do have a couple interesting news items. So Quentin, you're up first.
All right, perfect. So, an ambitious new Search for Extraterrestrial Intelligence Institute, or SETI, project seeks to identify signatures of advanced alien civilizations, not by studying individual stars or star clusters, but entire galaxies. So, this project is entitled Breakthrough Listen, and it combines data collected by the Robert C. Byrd Green Bank Radio Telescope in West Virginia, the Parkes Murayang Radio Telescope in Australia, the Automated Planet Finder Optical Telescope at Lick Observatory in California, and the Meerkat Radio Telescope in South Africa. The program involves a survey of the 1 million closest stars to Earth, as well as the center of the Milky Way galaxy and the entire galactic plane. And crucially, it also includes a survey of the 100 closest galaxies to ours. So there are trillions of stars located within this data set. Both within the Milky Way and near the centers of these neighboring galaxies. And what the researchers did is they searched for radio technosignatures in 4 frequency bands from all of these stars. So, what exactly is a technosignature? It's a radio signal with characteristics that we would expect from a technological source. So, a radio signal a few hertz wide that exhibits frequency drift, which means that the transmission source is accelerating relative to Earth. Because it'll either be moving toward or away from the Earth, this will cause it to be red or blue shifted, causing the frequency to drift over time as a result of this acceleration. So satellites in orbit, deep space probes like Voyager, or transmitters on a distant planet, they should all produce radio signals like this. The SETI team found 1,519 signals that could not be identified as just radio frequency interference. But careful analysis of these signals showed no evidence that any of them were likely to have been produced by a technologically advanced alien civilization. So that's a little bit disappointing, but does it mean that there's no advanced life out there? Well, no, not necessarily. It's important to note that while examining whole galaxies allows us to cast a much larger net when we're searching for life, so to speak, it also means that only the most powerful radio signals are actually detectable. So any technological signals that Breakthrough Listen would be able to detect would be far more powerful than anything the human race is even remotely capable of producing right now. Breakthrough Listen should be able to detect a signal with a strength of 10 to the 26 watts or more coming from the most distant surveyed galaxies. 10 to the 26 watts is a 1 followed by 26 zeros, which is roughly equal to the power output of the sun. So a civilization would only be able to produce radio signals this strong if it had developed a means of harnessing the entire power output of a star, which would make it what we call a Kardashev Type 2 civilization. Humanity is obviously nowhere near this level of power consumption, and it's important to note that the Kardashev scale is entirely hypothetical. It's possible, for example, that highly advanced spacefaring civilizations may exist, but they do not need to generate such immense quantities of power in the first place in order to communicate. So it's important to remember that Breakthrough Listen is not capable of detecting civilizations at a similar level of development to our own, but only those at an exceedingly high level of development that has only been hypothesized. And the fact that they didn't find any doesn't rule out the existence of extraterrestrial life altogether. It just shows that there's no evidence of any particularly powerful Kardashev type 2 civilizations within the nearest 100 galaxies. Nonetheless, the project represents a uniquely ambitious search for the most advanced extraterrestrial life, which serves as a complement to the pre-existing searches for lower power radio transmissions from nearby stars. It also places some important constraints on the presence of technosignatures in nearby galaxies.
This is a really cool way to search for extraterrestrial life. Like there's so many different ways that you can even look for some kind of signature of life from different exoplanets, but this one, just looking at entire galaxies, is really, really interesting.
Yeah, it really is. I think that what's most interesting about this is it almost it kind of seems to prioritize searching for like the most like technologically capable civilizations possible first, which I think is an interesting approach. Um, most of SETI's research up until this point, it does search for either any kind of evidence of like Dyson spheres, which are essentially big swarms of satellites that orbit around a star and collect energy from it. Which, in theory, if these things exist, if there are any civilizations capable of building them, would cause a decrease in the light output from the star in a way that we should be able to detect. Or they do what Breakthrough Listen did, which is attempt to find radio signatures from communications from these civilizations. But radio communications, I mean, first of all, we don't even know if there's some higher level, more efficient way of communicating, like beyond radio, that we might discover someday in the future. This is all extremely hypothetical, but if radio is the best you can do, it doesn't really discriminate between comparatively weak radio signals like the kind we're already using, or extremely powerful radio arrays that are designed to communicate between star systems. So I think what's really interesting about the search for extraterrestrial life in general is that it almost tells us more about ourselves than it tells us about the life that we're searching for. Because in order to even carry out the experiment, you have to make some assumptions about what an extraterrestrial civilization would even look like and what you should be searching for. So it's kind of a creative exercise in the first place to imagine what an extraterrestrial civilization, how it would operate, what its priorities would be, what kind of mark it would leave on the universe around it, and then try to search for that. It's kind of working backwards, but it's all we can really do because we only have one intelligent civilization that we know of to base this off of, which is humans,
Mm-hmm.
right? So
Mm-hmm.
it's very much trying to extrapolate from a sample size of one, in a way that's very complicated, and it has all sorts of philosophical questions kind of rolled up into it. It's really interesting, really really interesting.
Absolutely. I can't help but wonder when we talk about things like this, like what would happen if scientists came out and said like we actually found what we think are legitimate signs of extraterrestrial life. Like
Oh boy.
I I'm not sure I don't think a lot of people would believe it, honestly.
I mean, given given the way people reacted to those those supposed alien mummies that they found in that desert, I mean, it does kind of seem that way. Uh,
Yeah. Yeah.
uh, yeah, I mean, it's even we have found like really strange signals before, like the wow signal, which we still don't have an explanation for. And there's always the people who want to say, oh yeah, this is definitely aliens, and it's not necessarily like the most uh, academically honest way to approach the question, just always assuming it's aliens. But
Hmm.
it, there, I think that if we do detect a signal from an extraterrestrial civilization, I think we will not have any kind of consensus on what it is for a very long time.
Hmm.
Because this is a very big question, and it's kind of an extraordinary claim. Oh, we've discovered an alien civilization. Extraordinary claims require extraordinary evidence. So
Hmm.
yeah, it is one of those questions that even if we do find something, it may take us a very long time before we're sure we found something. And that's just kind of the way that the science works. Yeah. I mean, as fun as it is as nice as it would be to conclusively point and say we found intelligent life out there. It's probably going to be a lot more. We're probably going to have to be a lot more cautious than that if we want to be responsible.
Oh, absolutely. I can even see sort of similarities with some like discoveries of, not aliens, but just some other scientific discoveries of, like you can discover something and it'll be a tentative detection for a
Mhm.
while, and then you have to wait and gather more data before you can say conclusively what it is, which can take a very long time, even for things that we're used to studying, like galaxies. So
Yeah,
definitely will take a very long time with alien civilizations as well.
yeah,
Um,
as we should, honestly.
oh yeah, yeah. But on the topic of life on other planets or on other sort of beings in bodies in space, there is an interesting discovery out of one of Saturn's moons, Enceladus. They have not detected aliens, they have not detected extraterrestrial life on Saturn's moon, Enceladus, but there has been an interesting new detection of a molecule that is an important precursor for the building blocks of life. So, just a little bit of background on why Enceladus is awesome and why everyone is studying Enceladus is because this moon is really wild. Like, it is far from just kind of a dead rock in space like our moon, if I could say that. It has this massive subsurface ocean that is spewing water in these plumes out into space. And these water plumes have been studied for a long time to learn about their composition, to see if Enceladus and its subsurface ocean might potentially be able to harbor some kind of life. In the past, particularly in 2017, scientists discovered evidence of things like carbon dioxide, methane, sorry, and hydrogen in the plumes of the water plumes from Enceladus, which are all kind of important molecules for life. They don't necessarily indicate that there is life on the planet, but they are all important molecules that, for life like humans. So it was definitely a really interesting and kind of encouraging result that put Enceladus in this light of it could have the potential to harbor some kind of life. But now scientists have gone and reanalyzed data from NASA's Cassini mission to Saturn. This was a Saturn orbiter that ended its mission in 2017. But going back and reanalyzing some of this data, scientists have now found evidence for hydrogen cyanide in these plumes, which is a precursor for some molecules for life. So, in particular, it's really important and is really good at helping to create amino acid, which is amino acids. And these are like fundamental kind of building blocks of life. It has the existence of hydrogen cyanide in these plumes. If their source of the hydrogen cyanide is the actual subsurface ocean in Enceladus, could also indicate that there's more energy available for life in the subsurface ocean than previously believed. So while this discovery has not like definitively said that they have found life on Enceladus, it is definitely sort of painting this picture of Enceladus of this could very well be able to host some kind of life. Not like intelligent life like humans kind of thing, but could very well be things like smaller kinds of microbes maybe or something that are lurking under this subsurface ocean on Enceladus. So the research is also very important because it now allows scientists to study in the lab how certain complex biomolecules might be able to form on Enceladus. So definitely a lot of cool research is also going to continue coming out of this discovery in future.
I think this is one of those examples of something where like the science has progressed really far, even over the course of my lifetime. And I'm only 24 years old, but I remember when I was a kid reading about the solar system, everything was saying, oh, there might be a liquid ocean under the ice of Europa. And now we know, like, not only is there a liquid ocean under there, but all of these moons, like dozens of moons, have or most likely have liquid water under their surface somewhere. So,
Mm-hmm.
like, I'm very optimistic that there's some kind of life on at least one of these things, or at least I really hope so.
Absolutely. And especially when you think of like if if other stars have solar systems that are at least in some way similar to ours, you're not only searching for life on the surface of that planet, but their moons also. Like there's been so many Jupiter, Neptune size exoplanets that have been detected, like their moons. Look at their moons. If all of the moons are interesting things, or at least some of them, like the moons that we have in our solar system. Like that's an entirely new place to look for life, which unfortunately I don't think we can do exomoon observations quite yet, but maybe soon.
All
All right.
right.
Yeah, well, we are just reaching the end of the hour here. You've been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Quinton and myself, Sana. You can always connect with us on Twitter at the handle at York Universe, on Instagram at the handle at York U Observatory, and on Facebook at Allan I. Carswell Obs. You can also check out our website for show notes, content updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in. We will see you again in the new year. Clear skies and have a good night.
Good night.